Hello there, science folks. My name is Brandon Pruitt. I'm the sales engineer here at Pasco Scientific, and today I'm making this video to demonstrate how to set up and use the Hall effect experiment. And I will also be going over some measurements and explaining some of the calculations that are involved. So let's start off by going into the apparatus. Right here we have our 40 centimeter steel track with blue tape measure, measured out in centimeters. And on here we have attached our Passport 2-axis magnetic field sensor. This is connected to our 850 interface here, so we can display that data in our Capstone software. In the middle here we have our electromagnet. This creates a magnetic field that will be passing through our semiconductor slab where we're taking measurements. And right over here is our Hall probe. This essentially is a printed circuit board, where at the end of it we have a little microchip soldered in there, and all that is a slab of semiconductor material. In this particular case, it's gallium arsenide. It's worth noting on there's a little diagram in white. We have a little white rectangle there, which represents the semiconductor material, and we have labeled the probe current that will be going through that material in a direction. It goes from top to bottom here. And then we have the Hall voltage that is measured transverse to that current, with the positive reference on the left-hand side and the negative reference on the right-hand side. So that's the physical apparatus. The electrical components are right here. This is our Hall effect apparatus. On here we have two current supplies and a voltage probe. To start off, we'll connect the voltage probe, which is measuring our Hall voltage, through our probe here. And that is connected just like this here on the right-hand side of the probe, labeled use of H, the same exact labeling that we have here on the apparatus, so it's very hard to mix them two up, and everything's color-coded. On here, we also have two other outputs for the Hall voltage and Hall current. These two outputs are connected to our 850 interface, so we can display the data for the Hall current and Hall voltage in our Capstone software and then analyze them. In the middle here, we have our Hall current. This is the current that goes through our probe here, and that ranges from 0 to 10 milliamps, and just uses standard red and black patch cables. I'll connect those here for you. Once again, the labeling is the same. I sub S matches I sub S on the apparatus. Plug those in. And the last of our current supply is the excitation current. And this is the current supply for our electromagnet. Now you'll notice that these cables are shrouded. Reason being is because the current range on here is high enough to be dangerous. So it's important that these are shrouded for safety. And so that's how you make all the connections here for the apparatus. So now if we go into Capstone, if you go on our website, pasco.com, and look up the Hall effect experiment, you can download the pre-configured Capstone file. This is what it will look like when you first open it. So now I'm just going to dive right into taking measurements. So to begin, we have two different ways in which we're going to verify that the Hall voltage and Hall effect are in fact true and correct. We have a general equation, and we're going to be looking at the current through our probe and the magnetic field produced here. Those are the two variables that will be varying. So first we will start by varying the current. And this is the pre-configured page. So to start off, I'm going to move the Hall probe roughly into the center of the electromagnet here. And we're going to tighten that clamp down. And this is up to you. We need to establish a magnetic field in that electromagnet. So I'm going to start off by supplying a 250 milliamp current through there. And this is going to be held constant for this portion of the experiment until we do another couple runs, by which point you want to change it. So we'll set this to 250. And make sure you reference either the table data in the software or the display on the Hall apparatus, and just make sure to keep it consistent when you're taking your measurements, because there's a very slight variance, 0.1 millivolts, 0.1 milliamp, if that. All right, so we've set up the magnetic field. So now what we're going to do is we're going to hit preview, and we'll have a live data capture of the Hall voltage at any given time. So now what I'm going to do is we're going to increase the Hall current through the device in 0.5 milliamp increments, and after each increment we're going to hit keep. And we're going to take about 10 data points at least until we get up to about 5 milliamps of current. So we're going to do the first one. All right. And we'll hit keep. And then do the next sample. Up to 100, up to 1 milliamp. Keep. And 1.5. Keep. Oops, missed it. There we go. And 2. 2.5. 3. 3.5. And 4. And keep watch of the graph as I'm incrementing the current through here. So you see something quite interesting with the transient response for this until it reaches the steady state for each increment. 4.5 and 5. All right. So now we've collected our data and we have a nice straight linear curve that relates the current to the probe and the Hall voltage. So what we're going to do now is we're going to reduce the Hall current all the way back down to 0. And now we need to record the intensity of the magnetic field for this particular run. So we're going to remove the Hall probe out of the way. Then we're going to take our Passport magnetic field sensor. Make sure you tear it first. There's a little green button right on here before you move it into the field. And same thing at roughly about center. There's actually a little white dot right here on the probe. And that tells you exactly where the center of the sensor is, so you have an idea of where to place it. So go ahead and place that in there. And we see we have at 250 milliamps of current, we have approximately negative 0.019 Teslas. And so we're going to record that in here. We're going to change this to 250. And I'm going to record the value. 0.190 Teslas. Okay. And you'll be going back and using this data later. So for now, we can hit stop. And you want to do this run about 2 more times at different magnetic field intensities or field currents. I have to choose 500 and 750 just because they're even. So that's the first step in varying the current. So the next step for this experiment is to now vary the magnetic field. Before we do that, make sure you reset everything to off so there's no output anywhere. All right. So before we actually go through and vary the current through our magnetic field, we actually need to establish the equation for the magnetic field, because that is directly dependent upon the current that's going through the coil. So in a very similar process, we're going to keep the Hall probe out of the way. We're going to tear our magnetic field sensor and place it into the field. Make sure you tighten it down. And just like the previous step, we're going to this time adjust the excitation current in increments of 50 milliamps and record the consequential magnetic field strength. So I'm going to go ahead and hit preview. All right, beautiful. And we're going to increase this up to 50 milliamps. And we're going to hit keep sample. And go up to 100. And 150. 200. 250. 300. 350. There we go, and 400. Now you'll notice the graph has two curve fits on there, one cubic and one linear. I'll explain that in a moment. And 450. 500. 550. 600. 650. 700. And that seems to be enough data points, so we'll go ahead and stop right there, even though there's more room. So now what we're going to do is make a general equation. So we have two different curve fits on here. One is linear and one is cubic. The reason being is some electromagnets are not linear, so this just covers all the bases. And if you zoom out on the graph for the curve fits, you can see that for the cubic, we are on the linear region. And then if you compare the M value on the linear curve fit to the B value on the cubic fit, you can see that the coefficients are very much the same. So we can regard this as a linear fit. So now we have defined the magnetic field with respect to the current. And now one other thing we need to go back and do is we have a little compensation to adjust for. So by the design of the probe, where the two voltage probe leads are placed on our Hall probe are not perfectly across from each other. So as you can see from the picture here, we're going to have a small voltage drop, so we need to account for this. It's going to vary from device to device depending on how it got soldered. So the way we record this is just like we would in part one for varying the current. We place our Hall probe inside the magnetic field, but this time we have no magnetic field going through it. So what this does is it isolates this potential difference. So we're going to go back to vary current, and I'm going to reset the excitation current down to 0. And just like the previous step, I'm going to hit preview. And I'm going to increment this by 0.5 milliamp increments. And we'll hit keep. Same thing, go up to 1 milliamp. Keep it. 1.5. And 2. 2.5. 3. 3.5. 4. 4.5. And 5. And we'll go ahead and hit stop. So if we look at our graph here, we can see that this curve is very, 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 very flat. So what this tells us that our offset compensation and placement of the soldering probes is actually really close to each other. It's practically negligible, but that answer is going to vary depending on what probe you end up using and how well it was soldered. And so what you'll do with this piece of information, you will subtract the slope of this value from all the other slopes of the other runs that you do for varying current. And those will be your actual Hall voltage measurements. So now let's go back to the B equation here. And now we're going to set up the equation for varying B. So I'm just going to use the linear fit for this one since it works very well. So we're going to do negative 0.755 or 0.755 into our calculator. So we'll go back over to vary B, and we're going to open up our calculator here, and we're going to get rid of all these other terms except for the I to the first power. And we'll make that 0.755. And hit enter. All right, so now we can actually do a plot of the magnetic field strength with respect to the Hall voltage. So what we're going to do for this experiment is just in converse fashion, we are going to set up the probe current to some fixed value. So in this case, we'll do 2.5 milliamps. So I can get it. There we go. And then we're going to increment the excitation current by 50 milliamps and use the same recording process that we did for varying current. So we'll go ahead and hit preview. Then we're going to move this up to 50 milliamps. And we're going to hit keep. And then we'll go up to 100. 150. 200. 250. 300. 350. 400. 500. Oops, my apologies, 450. There we go. $550. And we'll stop at 6. So you get the idea. All right, beautiful. All right, so once again, we see a very nice linear relationship. And you'll do this at least 2 more times for a different Hall current. And in here, record the Hall currents that you use for each run, and then label which run you're referring to. So you can go back and do your calculations later. And that just about covers it for the Hall experiment. With this data, you can go to the analysis page and plug in all your numbers for the equations that are asked of you, and you will verify that the charge carrier density, if you've done this right, will be very close to the same. And that's how you do the Hall effect experiment.